Yeah, I wonder.
Okay, so it's a pleasure to have Professor Lehner from the Perimeter Institute, one of the uh, really leading experts in strong gravity, and he'll be telling us about non-linearities and gravitational signals from black hole spacetimes. So please.
Thank you. Thanks for coming. So, given the audience, this will be more like an intimate talk, and if I need to use that side of the blackboard to make some drawings. The talk is kind of strange because I'm combining different topics into one. This is kind of following my train of thoughts lately in trying to understand some features, both for practical reasons and also because I've been wondering about how to understand a beautiful theory like general relativity in a dynamic regime. Like, through the combination of efforts through many decades, we've learned a lot about the theory, but we've learned about things in very special situations or asymptotia. But what happens in the very nonlinear regime, it's a question that we need to, that I like to address. And I would argue that the tools that we typically use to study those regimes are typically inadequate, and I'll tell you why. And the reliance or the over-reliance of those tools might actually risk coming up with the wrong messages once we analyze, for instance, gravitational waves that are being detected. So this is hopefully what I'll try to convey. And if I manage to do that, then I will be trying to argue we need to look elsewhere to get some guidance, at least, or a motivation for how we can try and understand the theory, at least in these regimes that I'm interested about. This is not to say that this should be a complement of everything that traditionally the field has been doing. So I'll try and describe a little bit of the motivation of where is it that I'm coming from, and primarily it's motivated, of course, by the detection of gravitational waves and what is it that we're trying to do with them, as far as trying to poke into the theory itself and have very strong tests of general relativity. I'll say that, well, as we try and move into the nonlinear regime, and why is it that we care, there will be some challenges that we need to address. And then I'll motivate going to kind of contrast and get inspiration from hydrodynamics in more than one way, and why is it that I go there, and maybe what the promise might be. And there will be a potentially crazy idea that I will throw out there. That is something I've been investigating on and off for already kind of a decade without a good idea. So maybe one of you will, if you find it worthwhile, might be the one that finally resolves it. And then I'll go back to basics and then try and see how we can bring everything together. So of course, the main motivation is we're detecting gravitational waves through the combination of detectors on Earth so far. We also have evidence from pulsar timing, but as far as looking at the individual waveforms or waveforms coming from individual sources, we're using the gravitational wave detectors on Earth. And as I'm sure you've seen, it is an example of the first gravitational wave that was detected. You see that, okay, the oscillations or the strain is showing some ramp up in frequency and amplitude. Then this is where we regard the merger has happened, and then the relaxation towards the ultimate solution that seems very well described by a Kerr black hole in consonance with the no-Hare theorems. But of course, this is a unique opportunity to gain a better understanding of what the theory has in this very nonlinear regime, very highly dynamical. And in particular, I'll describe some tests that rely on understanding very well this late time behavior. So as the merger takes place, the form object is trying to relax down to the ultimate Kerr solution. And there is a lot that is writing on trying to understand very well what this is. But then I'll describe and remind you what are the tools that we use or we rely to try and understand this regime. And then I'll try and poke holes on it. But ultimately, also, I'll try, and this has to do with this crazy idea, to connect, when we look at this, this is a very simple looking waveform. We're having two black holes that are colliding with each other at a very large fraction of the speed of light. We have, as far as say one black hole is concerned, we're perturbing its spacetime with something of order 1. And yet, the gravitational wave, of course, we have the luxury today to say, well, they're rather boring rather boring looking. We don't see anything very, very complicated here. Just to keep going with the analogy of hydrodynamics, if we have a nonlinear regime in hydrodynamics, we know turbulence takes place, and the typical image that one has in that regime is that we form vortices, those vortices break into two, and this keeps going on in a cascade till eventually we dissipate that energy elsewhere. So this is a very strange kind of setup where we have one nonlinear theory that display all this richness, while these other ones is rather mundane. So let's try and see if we can say something about that. And in the process, we're going to both challenge a little bit what is it we're trying to interpret this signal with, and also challenge our idea of this turbulence in hydrodynamics and why is it that we think a particular behavior is going to take place when in reality it's actually a different behavior for the case of interest. So let's move on. So first, okay, just to remind the tools that we have, assuming we can live in linear land, in particular, if we're assuming that we have a black hole described by the Kerr solution, the typical way to try and understand perturbations is to have some small field where we write a full metric in terms to first order in this small field. And if we plug this into Einstein's equations, we choose the right gauge, we understand that the solution to this field essentially is a box operator acting on H. And if we put the correct boundary conditions, which is gravitational waves are going at infinity or falling into the black hole, on a non-changing background, the Kerr Black of mass m and spin a, then these the solutions to these equations are known as quasi-normal modes. They're described by exponentially decaying oscillations, and both the rate of decay and the oscillatory frequency is tied uniquely to the mass and spin of the black hole background. Of course, this is a linear analysis. It relies on having had the guts or the goal to think that the black hole at some given time can be well approximated by a Kerr solution plus a small perturbation. Because the LIGO-Virgo-Kagra scientific collaboration uses this in many ways in the test. One is to, let me go back, is to rely on very early on post-Newtonian approximations, obtain what the mass and spin of the individual black holes are, given the trajectory here, and solving the two-body problem. Then you can use this linear analysis of a fixed black hole background, which you think is described by some mass and spin, obtain the mass and spin out of the decay and oscillation, and then ask the question, are the two predictions consistent? So by looking at the spiral and using numerical simulations, we have a recipe that says if the individual black holes have these spins and this angular momentum, and they're coming in a quasi-circular trajectory, i.e. a low eccentricity, or essentially zero eccentricity, the prediction is that the mass and spin will be something. Then you go to the after merger and you explicitly extract the mass and spin from the decay rate and the oscillatory. And this is what you have from the post-in spiral. This is when you extract from after the merger. This is what you can guess from the in spiral as far as the final mass and final spin. And so then there is consistency in some regime. There is, of course, tension in some other. And eventually, if you use the full waveform, then you have a much better thing. But one of the things that we're trying to do, or we're hoping, is that maybe one day we're going to have deviations from general relativity. Something is not going to work. So if these two pictures begin to be to show a non-consistency with each other, maybe there will be hints of new theories. But the problem is that how well do we know the regime in which we can use a description in terms of a linear behavior? So we need to have good command to know from what point in the merger, from what point in here, can we use a linear approximation? We could try and use it very late on. That's when the black hole is essentially quiescent. That would be rather conservative and rather on solid ground. But the more we wait, the less signal we have, the more difficult it is. So there's a lot of interest to try and push as early as possible the regime in which this linear description is applicable. The problem is the further you push earlier in time, say after the merger, the more delicate this question of whether you are justified in using a linear approximation or not. And so then we need tools to understand how to do this correctly. And there is a lot of tension or controversy going on at the moment because there is a claim by some groups saying we have already measured more than one mode. The importance of measuring more than one mode is what I said. Every single mode of the decaying exponential and the oscillatory decaying exponential can be used to extract mass and spin. So if you measure two of them, then you can have already a very strong constraint of general relativity. And so that's part of the reason why there is a lot of interest in this. So that was kind of the motivation. And I'm going to just make some observations, which all kind of ride on this question: when does the system start behaving linearly? And what risks arise if this regime is not correctly identified? Where and how a linear analysis will break. And we have already had several hints of this, the linear analysis breaking down one way or another. So one is this very beautiful work by Stefanos Aritakis that identified in the extreme black holes and linear instability. So already perturbations in an extreme black hole show divergence of the curvature on the horizon. This is not happening in the substremal case, so one could imagine thinking this is a red herring, but let's go at second observation. Well, one can work out second order perturbations. So if we go back here, ask what happens if I add a second order, which will be sourced by this first order field. And if one works that out, and this is a long history, but the latest works are by this group of people that show that second order perturbations are sourced by the first order mode, and then begin to see new modes that you wouldn't have expected from a linear analysis. And a third observation, this is something we did a couple of years ago, is just imagine if you insist of believing that a linear approximation takes hold or is applicable. So somewhere here, if I draw infinity, there's this late behavior of an exponentially decaying oscillation, which is a solution of the problem I just described, linear perturbations of a black hole background. Then I know the solution not only here, I know the solution all the way through the space-time, but in particular, I also can ask, what's the flux of energy and angular momentum into that black hole? And when you do that calculation, then you realize that the mass is changing by a few percent, even for that case I showed you, and the angular momentum parameter is changing by more than a few percent. So it's hardly the case that you could say the black hole is unchanging. Already, if you want to do something better a few percent, you know that's not going to be possible. So what we want to do now is try to say, well, how can we go to nonlinear land, and what tools can we use, what intuition, and maybe in doing so, it will push us in a particular direction, and perhaps we can get some new phenomena out of it. So of course, we do have a tool to do that, and these are numerical simulations. We can just solve the equations of motion, Einstein's equations of relativity, in its full generality. We can get very accurate solutions, but of course, these are numerical solutions. We can say, for these situations, this is the way the waveform looks like, but we'd like to know better. We'd like to understand, perhaps, if we can, through first principles, this simple question: why is this waveform so simple? That's what I'd like to know. What mediates this very strong scenario, just giving such a simple looking waveform? Why is it that we have that? So an example of where numerical simulations have been tremendously impactful is in the discovery of critical phenomena in general relativity. That's perhaps, I would say, still is to today the poster child of what the power of numerical simulations is. But the power of numerical simulations is not to find a new solution, it's to, given that solution, push the envelope in our understanding of the theory itself. And this was beautifully illustrated by this. Not only Chopwick found that solution, but this opened up the door to many, many interesting studies that followed, motivated strongly by the observations from numerics. So, short of knowing what else we could do, one can then look at a field that has been dealing with the nonlinear regime for much longer than us, and that's hydrodynamics. Of course, hydrodynamics in and on itself has a long and yet unfinished history, of going after nonlinear phenomena, creating new tools, sometimes even looking at things statistically, but overall trying to address that. Why? Because they have very, very important or very valuable reasons to go for. In particular, we put planes in the air using the equations of hydrodynamics. We better know what we're doing. And even though we don't know a lot, there is quite a bit of information that has been coming out through many decades of work. So there are key observations with respect to the transition between linear and nonlinear phenomena. We describe this with either laminar or turbulent flow. We have something like a Reynolds number to identify the different regimes. We identify energy cascades, different ways to try and understand mode couplings, how energy in one mode wants to transfer or moves into another mode, and in some cases, going to go to the UV, in the IR, and these are things that we could at least get some intuition or some motivation on. And so let's just bite the bullet and see what we can learn there. And this is not, of course, this is not the new idea. This has been, in some sense, very much pursued since the 80s. At that time, people were also having kind of the same thoughts. How do we understand the type of solutions and the behavior of physics in a theory that is very complicated and rather obscure at that point? In the 80s, people were trying to say, well, can we understand Einstein equations in a different tone? Can we make an analogy, at least in some regimes, of Einstein equations into things that we know a little bit better? So this was this, if you want, program started in the 80s by Damour, where he essentially, and I'm going to tell you a story and then I'm going to correct myself, but essentially imagine a time-like surface very, very close to the horizon and saying, what is the projection of Einstein equations on that surface? And if you do so, and identify the right variables, you lo and behold, Einstein equations projected on that surface gave rise to Navier-Stokes, were dual to Navier-Stokes. In reality, Thibault did it first with respect to this null hypersurface. And the equations are very complicated, and we're going to get there. And for that reason, then people decided that, well, maybe it's because there is a degenerate metric, this is a null surface, let's pull it off into some time-like surface that is closed, and this is where you get Navier-Stokes. But at that point, these equations were not understood. Of course, then this kind of came back with a very strong impetus in the early 2000s when people started thinking very seriously, coming from string theory and in ADS CFT or gravity in ADS. And if you do the same thing, but rather than projecting Einstein equations on a time-like surface in the bulk, you project things on time-like surface at the infinity of ADS. What you get here is special relativity. Special relativistic hydrodynamics. So here you got Navier-Stokes. Here it was relativistic hydro. And now I'm going to go back to the current time where people realize if you do some funny limit. So here, let me start here. If you look at relativistic hydrodynamics and ask what's a group of symmetry underlying the equations of motion, is the Lorentz group. If you imagine taking the cone or opening the cone by taking formally the limit of the speed of light going to infinity, this ends up giving the Galilean group. And the group that governs hydrodynamics, and that gives you the Navier-Stokes equation. But you could do the opposite. You could say, let's close the cone, take C to 0, and ask formally, what does happen? So first, on the mathematical level, of the group of symmetries, it's a so-called Carolean group of symmetry. And the equation of motion here give you this so-called Carolean hydrodynamics, of which there is quite a bit of work, maybe formal, for no particular reason, but just to try and understand what that limit is nowadays. But funnily enough, we're going to encounter it in a few minutes and then also try and motivate something else. So let me start first by going here and making some claims of why is that we care about doing this and what the message might be. So if you take relativistic hydrodynamics, and as I said, and you take gravity and Einstein's equations and project them onto that boundary, what you have is Einstein's equations. And now there is, you have Einstein's equations, what you have is relativistic hydrodynamics. Now there is a tension that immediately comes in there, because for a long time people have understood both hydrodynamics, relativistic hydrodynamics, and Einstein's equations as being very distinct theories. Einstein's equations, we know, solutions do not develop shocks. And that's because we have propagation, perturbations propagate at the speed of light. There is no crossing of characteristic. How can that give rise to the phenomenon of turbulence, even though they are decoupled? These are the kind of arguments that people were making. But as I say, ADS-CFT motivates and makes rigorous gravity fluid description, and I'll say a few words in a second to make it more explicit. But one thing that this new kind of revisiting of the memory paradigm had in its core is to think of a new way of doing perturbation theory. The typical tools of perturbation theory that we use in GR is the one I mentioned before. Imagine the metric is given by a background metric plus some field. This guy did a completely different type of perturbation. They said, well, imagine you have a metric that is describing the space-time of a given solution, and now promote that metric by taking the constants of your metric. If we were thinking of curve, and you have the mass and spin, promote these things not to constant anymore by functions of the space-time coordinates themselves, and assume that you're probing a regime where gradients of some given order are subleading with respect to lower gradients. So this is a gradient expansion perturbative approach, which is different, as I said, from the typical one that people use in Einstein's equations. But this comes very strongly motivated by effective field theory considerations, and you can say, well, let's go and see what happens. So what you take, or what they take, is a boosted membrane, black brane, that has a given velocity u and a given, say, size b, or temperature given by this quantity b. Promote this to now functions of the space-time coordinate, project them onto the boundary of ADS, and lo and behold, what you have is exactly relativistic hydrodynamics. It was worked all the way to second order. So at first order, in the gradients of the field, you have a shear viscosity. This coefficient, this transport coefficient, is given as 1/4 pi. This is something that comes naturally from general relativity. But it also has corrections at higher order worked out. You compare what this dictionary gives you to what is known in in relativistic dynamics. It was a 1-to-1 correspondence all the way through. So this was rather surprising, but it tells us that in some regime, and a regime of a long wavelength perturbations of black holes, Einstein's equations on the boundary are nothing but relativistic dynamics, or vice versa. And so naturally you say, well, wait a minute, given that I have made contact with hydrodynamics, could there be the phenomenon of turbulence? Because in turbulence of relativistic hydrodynamics is delicate in its own right, but we remember that if we take a non-relativistic limit, we are required Navier-Stokes. We can ask the question, are we in the right regime for turbulence to arise? And the answer is yes. Because then you might say, well, but that was in the Navier-Stokes limits or in the non-relativistic limit. What happens in the relativistic case? And I'll show you now some examples of that. So let me show you first this work. This is a work by this group of people where they took Einstein's equations, again, in 3+1 gravity with boundary conditions or a negative cosmological constant. You perturb the black hole with a long wavelength perturbation, and what you're doing here is going to infinity and saying, what's the vorticity of the gravitational field, and you get this. And I'll show you some. So this is some structure. Yes? Yeah, you have exactly ADS. Yes, it's anti-de Sitter. At infinity, it's anti-de Sitter. But why do they do this? They do this because a year earlier, we have taken, like, us coming from the gravitational side, said, this is weird. Are you guys, this program, I need to understand a little bit better. So what we did is to take, this theory, the boundary theory, or the relativistic hydrodynamic boundary theory, use the dictionary, because this is what this whole process, if you have this dictionary, you can reconstruct the metric of this full space-time. And so that's what we did here. We just solved the hydrodynamic boundary theory, obtained the solution, and then using the duality, reconstruct the full space-time at any point in the space-time of the bulk, evaluated the residual of Einstein's equations, and corroborated that everything was fine, that we were obtaining a solution, a bona fide solution to Einstein's equations with those boundary conditions. And what I said about the cascade, so what happens as time goes by? This is a moment of time. But if you wait, so this is the vorticity of the field at infinity. This was the initial data, was just some wiggles for no particular reason we chose them. But as time goes by, then you generate these kind of eddies. They begin to kind of show rotation of both signs. Red is one sign, purple is the other one. And this is a snapshot somewhere in between. But as you wait, eddies merge into larger ones, and eventually you just have two. And so remember, we said the picture of turbulence that we usually have in our hands is wrong. It's not true that vortices break into into smaller one and smaller one, etc. This is only true if we're talking about 3 + 1 hydrodynamics and above. Hurricanes have this large structure because at some point, the height of the atmosphere is irrelevant with respect to latitude and longitude scales, and the cascade begins to go in the opposite direction. Yeah, this is weak turbulence, and that's a spherical symmetry, and this is just mode coupling, but there is an interesting connection, but this is not related to that, because those are kind of collinear modes. These are modes that are not collinear. But it's interesting in that there, if one could introduce a particular approximation, this 2-time scale expansion, this is something I think we were the first ones to do it, that shows this nonlinear coupling is beginning to send energy in a particular way, but that can only go in one direction. This is going in the opposite direction. This is full nonlinear simulations. This is full nonlinear simulation done in gravity. This is full nonlinear simulation done on the boundary hydrodynamic theory. And with that, then reconstruct the full spacetime. And in particular, you end up getting things like this is some curvature invariance. And then what you see is that these eddies that in the boundary are showing some vorticity and some accumulation. When you ask what is that in the bulk, these are gravitational waves that have sufficient self-gravity to more or less keep themselves coherent in space and all the way inside, all the way to the boundary or to the horizon. So in some sense, they are reproducing or capturing these gravitational wave geons that Wheeler was suggested to do. Of course, they are not stable. They are slowly decaying away. In hydrodynamics, we would have viscosity, effective viscosity of the space-time, which is losing energy where? Into the horizon. As energy gets lost into the horizon, then this structure dies off ever so slightly or slowly. And that's the duality. And as I said, you can evaluate just by looking at solution at the boundary, what is the full solution in the interior, and then you have it complete. Yeah. Say again? Yes, there is a black hole. That's right. So this duality makes sense if you have a black hole, because then you have the temperature, the black hole has to be large, and you're thinking of perturbations, long wavelength perturbations of that black hole, of the scale given by that black hole. Yes? Yeah, this is related to Piotr's question. So in that case, it's pure ADS. Here we start with a black hole. And exactly, you put a mode and you see that gravitational interaction begin to move energy slowly to the UV. This, in this case, is moving energy a little bit into the UV, but primarily sending things to the IR. But okay, so there are two things I want to say that are important here. So first, if you understand the theory, the boundary theory, and you ask, what is the decay of the sound and shear mode? The description you have is exactly the same as quasi-normal decay. So the shear and sound mode of the hydrodynamic theory are capturing the lowest lying quasi-normal mode. The other one is, why does this happen? Why is that it went in the opposite direction? Why did it try to go into longer wavelengths? In Navier-Stokes, this is known. There is a quantity called entropy. When in the implicit case, it's conserved. Because it's conserved, it limits the way energy can move around. In particular, it limits the way modes can couple to move energy into shorter wavelengths. And in particular, most of the energy goes to longer wavelengths. So if this is true, if there is a relation of this observation to the relativistic regime, there should be, and this is pointing to the potential of there being a quantity akin to entropy in the gravitational sector that is mediating this behavior. So now, but that was ADS, and for those of us that work, gravitational wave, ADS is a cheat. I mean, we don't have a negative cosmological constant around that. It's a very convenient to do some interesting calculations, but the crux of the problem that I'm trying to do is just try and understand gravitational waves that are measured by, say, detected by LIGO. So, but first we want to say, well, we understand this duality and the consequence of this duality, largely in the asymptotic anti-de Sitter case. How much would this translate or have an impact on the asymptotic flat case? Because if I use my PDE hat, the addition of a cosmological constant does nothing as far as the coupling is concerned. It's a lower order term. It's not mediating coupling. It mediates time scales, but not the coupling. So it should still be there, be there in the asymptotic flat case. So let's go looking for it. So one is to try and say, well, let's just go back to our linear perturbation analysis and imagine black hole, send a gravitational wave or something to it, and then send another mode. For simplicity, we're going to send a scatter mode. But we're not going to say this mode is only seeing the space-time of the black hole that is unchanging. This scatter mode is going to propagate over the space-time that exists as a result of the linear mode perturbing the background itself. So what you then have to solve is an equation that has the box, so the scatter field will move will obey a box operator where the metric is a time and space dependent metric given by the first mode that propagates through this gravitational wave. So as a result, the operator can be written as a standard operator plus some time dependent operator, which comes as a result of that first mode. And then you study what happens with that field, and it turns out that because you have a time-dependent kind of operator here mediating thing, there is a parametric instability. So some modes will be able to extract energy of the gravitational wave mode and actually move energy into this scalar mode in a non-trivial manner. And in fact, for a transient time, you're going to have an exponential growth. And when this condition is satisfied, and this is just, it's a mouthful, forget about all the details, but essentially what you have in the left-hand side is the size of the gravitational wave perturbation divided by its azimuthal mode number and the decaying rate of it. And then this, you want to make it as small as possible, and you're going to make it as small as possible when the frequency of your main mode and the frequency of your scalar mode are in a 2-to-1 ratio. So it's already saying that some particular modes are the ones that will grow, and they are the ones that have longer wavelengths than the original one. So it's already hinting energy wants to go to the longer wavelength regime, not to the shorter wavelength regime. And this is just some illustration of what happens here. This is the main mode, and these are the modes that for a while satisfy their parametric instability. They grow, and after some time, this mode loses enough energy, you don't satisfy this condition anymore, and then from there on, all decay. But this has practical consequences. If you're looking at, if you think of the problem as a linear problem, you think that you put a mode, and the response of the space-time is the same mode out. Here it's not. It's some of that energy goes into other modes, and then a structure that you would have expected to be this and slow in decay begins to be much more complicated. And it gives backing to this idea that energy is trying to cascade at some modes in longer wavelength and not just stay in or shorter wavelength. So that was kind of observation number one. Trying to see what type of calculations we can do in the asymptotic flat spacetime that give us better control on or insights into this problem. Now let me do something else. I'm going to go back to, remember I said there were these equations that you take Einstein's equations and project them there. The equations were weird. Well, it turns out that these equations were exactly Caroline hydrodynamics. So if you imagine again, taking your conservation of the stress in your tensor, think of it as relativistic hydrodynamics again. But imagine taking the cone, close the cone, take the speed of light to 0, and just keep track of the orders of what you get in the resulting expansion. You end up with something that has a 1/c², something without c, and then something else that will automatically go to 0 as c goes to 0. Two sets of equations to satisfy. This H has to be 0, this HB has to be 0, and GB has to be 0. This is a rapid flash. Let me not go into the details for matter of time, but essentially what these equations end up is giving you this kind of structure. There is some energy of your Carolian fluid that obeys a particular kind of equation of motion. There is some momenta that obeys something else, and there are further pieces in the fluid description. So in contrast with your standard fluid description where you have energy, say pressure, maybe tied with an equation of state, velocity of the fluid flow, heat flux, and dissipation tensor, in the Carolian picture, you have a richer structure, but the same number of unknowns, energy and pressure. There are two currents and two dissipative tensors. And these are orthogonal to a vector. I mean, the natural flow is with a null velocity. And something that people in the Carolian hydrodynamic literature are wondering is how will this fluid thermalize? I mean, you have closed the cones. How is this particle able to talk with its nearest neighbor to tell them, hey, we should somehow get together and end up with the same state? I don't know about the general problem, but I do know that at least in the case of a subset of Carolian fluids that are dual to gravity, we can say something interesting. So if you take, let's say, if you take these equations and assume something, and imagine that you can have solutions where this Z and this J are 0, and we're going to make a few other identifications. The pressure, define it to be minus K, and this K will be the gravity or the inaffinity of the of the tangent to the null surface. Then the equations of motion that I showed before ends up being exactly these equations, which we will understand what they are. This is nothing but Wright-Chowdhury's equations for a set of null generators that are not affinely parameterized that kind of govern the null surface. And this other one is, some people call it the Hajicek equation, but in reality it's that equation that Damour got first when he started thinking about this membrane paradigm. And so then there is a duality. You can either try and get insights from Carolian hydro into gravity, vice versa, or use them to try and motivate some exploring the nonlinear regime. And this is something we have been doing lately with some collaborators, which I'll note next. So just before I get there, just the implications of Carolian hydrodynamics is dual to the null surface behavior in gravity. And if you imagine that you're thinking of a null surface such that asymptotically its expansion goes to 0, then we're talking about horizons. We don't have to, but that might be a condition that we want to pose. Incidentally, there's a lot of work that is being done with Carolian hydrodynamics because the same structure and symmetries are found in a null surface, or of course are also found on Scry. And so there is a lot of work that is going on in trying to identify charges, conservation laws, etc. In particular, having interesting messages to potential measurements of gravitational waves through memory effects. But of course, one of the things I'm keep always trying to go is that can we say something about entropy? Because I think that might it's some quantity that should be there in the gravitational sector, which we have yet to identify. So what we're going to do is just try and say, well, what can we go back and make contact with this nonlinear, or this tool to trying to understand a little bit more about the nonlinear phenomena that affects horizons and how that might tell us something about when and how should we identify the linear regime in, say, the post-merger of binary black hole collisions. So let's take this, let's say, a null surface, which we're going to soon fix it to be a horizon. Do an expansion that is in the local neighborhood of that null surface. So we're going to use a characteristic decomposition. This is the way we're going to write the line element. And we're going to use this coordinate rho to measure what happens off in the horizon in the null direction. And of course, out of that, the equation of motion projected onto the hypersurface are, again, the Wright-Chowdhury's equation and Damour equation. But these have some unknowns. So if I want to try and understand the behavior of this set of equations, I need to say something of what the surface gravity is. and what the shear is. So this, if I want to do the similar calculation of what was done in the asymptotic anti-de Sitter case, where one can understand how modes decay on the boundary, we don't have the luxury of separation. There we had a boundary at infinity that had intrinsic metric given by ADS. Here we're in the bulk. We're kind of really subject to whatever the spacetime is doing. And then in order to try and understand this equation of motion, they cannot be understood by themselves without having some information about what the bulk is doing. Yes? At this moment, it's completely general, but now I'm going to say let's imagine we have a Schwarzschild black hole and just perturb it a little bit, because we're just beginning to try and understand what we can do with this. And I'll show you kind of the first step, rather simple-minded. So the first thing we're going to say is, well, imagine we have a Schwarzschild black hole. We're going to assume that we're going to introduce a perturbation. This gravitational wave will go at some point. We're going to say this gravitational wave is a gravitational wave we know. It's a 2-2 mode or a 3-3 mode. And then we want to know what would be kind of the reaction or what would happen with this null surface, trying to, as much as possible, think of just what the surface is doing with enough information of what the bulk is how the bulk is affecting it. So for simplicity, we're taking Schwarzschild and assuming that every quantity has a expansion, and that epsilon would be some parameter. On the horizon. At the end, I'm going to put everything onto the horizon. But in particular, we have to involve this work with Jaime Redondo Juste. We have to involve the other Einstein equations. So these are the equations associated to the null generator of that surface. If I think of the orthogonal one, I have this further structure. But for, say, the stationary horizon or a static horizon, the expansion of this surface is 0, or the expansion of this null generator is 0. The expansion of the orthogonal one is a number of order 1, it's 1 over m. So a hierarchy gets kind of built in if I choose to kind of describe in this way. So if I look at this equation, let's say, to order 0, I mean, the expansion theta L is 0. So I can try and use this equation to get out of it what the surface gravity is. And I can do the same thing to connect the two shears. And if you go through that calculation, well, it's not difficult, mathematics will do it for you, then what you find is that you can write all these quantities, they say the surface gravity, the Hajicek or the vector that is orthogonal to the null vector on the surface that basically describes shifts from one slice to the next one, the intrinsic metric and the metric slightly off the surface, as function of that waveform that we're going to use these S's to incorporate. And all the other fields. And the fields that I want to maintain are, the expansion and the Hajicek. And once you put all that together and through some resummation, some smallness parameter. So you just do, it's a counting parameter, epsilon equals 0. So if I set it to 0, if I set epsilon to 0, I'm not perturbing anything. And then you put this into the equations themselves, and order by order, you try and obtain kind of higher order parameters in terms of sub epsilon value. So you just do, let me just say it in a different way. Put this back into Einstein equations, and order by order in epsilon, this is an order counting number, you have a hierarchy of equations. Yeah, we've gone to second order because the expansion of the surface is only cognizant to the gravitational wave at second order. First order just stays put. Thank you. So in particular, this Hajicek, obeys this type of equations. And this is essentially what one of the things we were trying to do is, if I look at these equations and I'm asking what is the H doing, and then, as I said before, initially when in the 80s these equations were obtained, people didn't understand what to do with them, because you have information that you have no control at. And even if you do, this is a very strange equation. This is like an ODE, and this looks like a PDE with some sources that it's hard to understand what the dynamics is going to be. But what I'm saying is that this kappa and the shear has in them some terms that depend on the main variables already in this guise. So if this allows you to kind of bring this to the forefront, and in particular, you end up with a structure like that. So you have this is like first, if I ignore everything else and I just think of this part, this is a diffusion equation with the wrong sign. It's blowing up. But of course, if I want to make contact with the horizon, I have to think it's still illogical. So I have to go to infinity and iterate backwards in the past. So this is saying some structure, as I get towards infinity, is just decaying away. But then there are also nonlinear terms on the edge. And if I use the same type of argument to define a Reynolds number, I can define a Reynolds number for these equations. When will the nonlinear features of this equation dominate over the linear features as far as the fields is concerned? And so then you can say, well, does this give you a picture that makes sense? And indeed, it does. So what you do, or what we do, is we go to infinity here, that would be I plus, set the expansion to 0, because we want, if it is a horizon, it should stop expanded asymptotically. Set this h to 0. And then we iterate to the past as a gravitational wave is about to go through. The black hole is teleological, so at some point here, even before the gravitational wave crosses it, begins to have structure to kind of compensate for what is going to be coming in and trying to satisfy that this is indeed a horizon at infinity. And so this is just an illustration of what this so-called Reynolds number is. As you go backwards to the past, it's getting larger and larger. And as that happens, you see a kind of an initial sphere with a very small perturbation develops more and more structure as you go towards the past. And one particular thing we were interested in making contact with is as you perturb, or as a gravitational wave, so if you imagine in the upside down picture, or let's say in the natural picture, and then we're going to turn it upside down, if at late times you think that your space-time is described by a black hole with an L equal 2 or an L equal 2 and an L equal 3 perturbation, what would be the features you're going to have slightly earlier as far as the structure of the gravitational wave is concerned? So in the upside down picture, we start here, we're going backwards in time. We imagine that at this regime, the space-time is well described by a 2-2 mode and a 2-2 and a 3-3 mode. And then we ask what happens earlier on. And so these are the modes that we put by hand to perturb the space-time. And these are the nonlinear modes that get generated by the interaction and the coupling. And so you have all these modes that are non-trivial, and you populate, and in particular, then this is just a way to illustrate that out of the 2-2 and the 3-3, you generate obvious one like 6-6, 4-4. This is just the square of the 2-2 and the 3-3, but a whole bunch of them as well. So some thoughts, I'm trying to wrap up here. So again, the significant portion of current fundamental tests of general relativity are tied to our understanding of the solution with a linear kind of picture in mind. And here is where we're saying we have to be careful. We have to understand well when the transition takes place, and these kind of ideas or calculations are hinting at perhaps a working way to understand where the assumption is justified. So, and particularly what we're trying to do is go after that question: when can we assume that a linear description is justified? Of course, more interestingly, is the detailed understanding of the nonlinear behavior might have hints of further and deeper tests that we can do, not only for physics abstraction, but to test the tenets of general relativity as far as the data is concerned. But more importantly, and this is where much of my work in the past several years has been trying to connect with, is this connection with hydrodynamics suggests not only different angles attack to these and our problems, But in particular, and then I want to go back to kind of the very beginning, can one understand the simplicity of waveforms by the existence of some quantity that somehow is limiting the behavior of the coupling for modes in the theory? And so I do think that there is this entropy idea is lurking in the back of something yet to understand. And there are different groups of people like Yaramos and Amos Yaron are working in Israel trying to look for entropy in some different ways in the context of graph and ADS. We're doing a different thing in a different way, Lauren Friedel and colleagues and Ina Flanagan. And I think we have yet to meet where we keep missing the mark, but somehow I think it's there. And I think it could have a strong influence in the way we understand things. In particular, as I said, I'm bugged by the simplicity of waveforms, and I think I need to understand that. So I think I'll stop here. Thank you.
Questions? May I ask a question?
Sure.
The instability you mentioned for extremal black holes, does it hold when you add matter to general relativity?
So you mentioned Aritaki's instability?
Yes.
Well, if you add matter, the problem is what are you going to do with that extremal black hole? And so if the matter is yet to cross the horizon, you still have the instability, but then that matter might change the extremality. So
No,
to the point that, yes.
Sorry, not probe matter. I mean, the fully nonlinear theory has matter. I'm actually thinking of supersymmetric extremal black holes,
Yes.
which are supposed to be stable. I mean, there's nothing for them to decay to.
Well, so what supposed to be stable? I don't know if extremal black holes are supposed to be stable. So you could make them naked, or you could kind of reduce the extremality. So if you perturb it, it's still a question as to what happens as you perturb it. So what you would expect if they are stable, if the spacetime is stable, is that you will reduce extremality. You're going to add a little bit more mass than, say, charge or spin, and then as a result, then it goes extremal. If it goes over extremal, then your theory breaks down, and we can't even answer the question.
Thanks. Questions not from me.
So I'm not sure if I understand correctly. Are you saying that this analogy between Einstein equation and hydrodynamic can help us to maybe dig further into this non-linear regime where we have to use numerical relativity at the moment. So yeah, I'm trying to see if it's possible to produce this this merger waveform with this method you just talked by transform these equations to hydrodynamic equation.
No, we can't, because it's in the wrong regime. So what we're using is understanding in a regime where you can use this analogy with hydrogen. Well, first, if I'm thinking, say, yeah, let me divide my answer because I'm about to mix two things. So if I'm thinking of black hole collisions in ADS, you have two black holes are colliding. So again, we're in a regime where now we're perturbing, say, one black hole with an arrow order 1 with a wavelength of about its same size. So in the context where the fluid gravity correspondence is well established is long wavelength perturbations of black hole. So there, that duality would likely be broken or would not be applicable at that regime. But if you wait a little bit more, then you're going to enter the regime, and then you can describe it from there on. Now, the Carolian picture, or if you want, you can forget about Carolians, if just the null surface structure and how perturbations they are behaving. So in principle, you could use. What I couldn't use is this kind of perturbative schema that we use to try and understand or dig a little bit into what the dynamics might be. So I couldn't use that perturbation. But if we were to understand in general how null surfaces are behaving with respect to the equations of motion that are intrinsic to that null surface with some ingredients of what is going on in the bulk, well, maybe you can gain some progress there. Of course, what might happen is you end up with a problem that is as complicated as the other one, but with perhaps some new tools or some intuition of what you'd be looking for. So an example is this one. Maybe I went too fast. Let me just. Yeah, so this one. So when we look for kind of this behavior, we were strongly influenced by the observations that in hydrodynamics, in the case of the de Sitter, there was an instability that was there just by looking at the analysis in where in the turbulent regime coupling should take place, and that should have some consequence. And so we decided to do this type of calculation, where we're saying, okay, let's just forget a little bit of the standard picture where the spacetime is unchanging and you have a field that evolves in it. Let's just look at the spacetime that is slowly changing and you have a secondary field evolving in it. And as you do, then you realize that this parametric instability takes place. And not only that, and this is, I forgot to say it, notice one particular thing is so if you wanted to be in the regime where the parametric stability was at play, then you would like to have this quantity as large as possible. And of course, this one as small as possible. So here I said we can make it as small as possible by the particular frequency of the modes that will be excited in the secondary mode in this 2:1 ratio. But then you can ask, when will I make this the largest? You will make this the largest if the size of the initial perturbation is strong, the azimuthal number description is as low as possible, and its decay rate is as low as possible. So from a point of view of partial differential or modes, nonlinear modes, what you're saying is, I want the mode to be there for as long as possible. We'll have a nonlinear theory, and that will be the most likely chance where nonlinearities will take place. But now I can just say, well, let's just make analogies with respect to what these ingredients are and ask what would happen, or what's the analogy in the hydrodynamic front. So this is the size of your perturbation, call it V. This is kind of the structure in space, so it's 1/m, right? So call it lambda. So the smallest the m, the largest the lambda. And this is the decay rate, call it viscosity over density. And this condition, being larger than 1, is nothing but the standard Reynolds number of hydrodynamics. So this was kind of looking for a particular case, finding a phenomena in general relativity, that then you can have a very natural understanding from the point of view of hydrodynamics. So motivated by hydrodynamics, go look for it in gravity, and then you get something that keeps reinforcing this intuition or this way of going back and forth.
Okay. Yeah, thank you.
We have time for more questions. If not, let's thank Professor Lehner for